This question from section 9.3, number 20, which is very similar to number 18, which probably hard to read. Let's zoom in a little bit there. Says the following. The wind chill index W is the perceived temperature when the actual temperature is T and the wind speed is V. So we can write the wind chill as a function of temperature and velocity. The following table of values is an excerpt from some other table. Use the table to find a linear approximation to the wind chill index function when T is near negative 15 degrees C centigrade, Celsius, whatever that is, and V is near 50 kilometers per hour. So we're looking at this spot right here. And then estimate the wind chill index when the temperature is negative 17 and the wind speed is 55. Okay, so we're trying to find a linearization. But instead of having functions to do it with, they're giving us a table and we have to like kind of estimate or find all the values. So let's remind ourselves what the linearization should look like. This is section 9.3, problem number 20. And again, very similar in execution to problem number 18. Let me zoom out just a little bit here. And scooch this up just a little bit. Okay. So to find the linearization, and our variables instead of x and y are t and v, it's the usual deal, right? It's the function evaluated at the input they're giving us. And I should point out that we're looking at a temperature of negative 15 degrees and a velocity of positive 50 kilo something per second, kilometers per hour. So our linearization is going to be the function evaluated at that point, negative 15 comma 50, plus the partial derivative in the t direction, evaluated at the same point, negative 15 comma 50, times the variable t minus the t value, which is negative 15. And then the same deal for the other part. It's going to be the partial with respect to f, sorry, with respect to v, evaluated at the same coordinate, negative 15 comma 50, and then multiplied by our velocity minus 50. So the usual kind of deal for linearization, right? Your z naught plus your partial times your x minus x naught plus your other partial times your y minus y naught. The hard part for this one is specifically estimating the partial derivatives, right? Because they're not giving us the function. We can't find the derivatives. So we have to estimate essentially the rate of change of the function in a certain direction at that point, which is, there's not a one way to do it. I'm going to do it the way that the solutions manual showed me how to do it because that's the way the other problem also works. But there's like a bunch of different ways you could estimate the rate of change. But here's how I think they want you to do it. So first I'll point out that, red pen. So this f of negative 15 comma 50, that's going to be that negative 29 right there. So let's talk about how to find the partial derivative with respect to t. So I'll remind you, let me see, I took some notes over here. Where'd they go? Yeah, there we go. So let's look at some partial derivatives here. I think I'm not getting too far off screen. I'm going to refer back to this, but yeah. So our partial derivative in the t direction, and we're going to try to evaluate this at the point negative 15 comma 50. So as a reminder, if we're taking the partial derivative in the t direction, the other thing is going to be held constant. So that 50 isn't going to be changing for this process. The negative 15, we're thinking of it as changing. We're letting the temperature change and seeing how the wind chill changes. So here's the limit definition version of this. It's going to be the limit as h goes to 0 of f of negative 15 plus h, comma 50. We're doing more work than we need to. Don't worry too much about this. Minus f of negative 15 comma 50, all divided by h. The usual kind of definition of a derivative, right? You just have a plus, you have your f of x plus h minus your f of x, all divided by h, taking the limit of that. And then the other input is just being held constant, right? Because we're differentiating with respect to t, not with respect to v yet. So now here's where you're like, well, how are we supposed to do this? So here's what they do. They essentially go to the next values above and below. And then they average those averages. So here's what we're going to do. We're going to look over here at, let me see, let me get the right colors here. So we're letting temperature change. So we're going to look at this point here and at this point here. So, and we're going to do them separately. So first, we're essentially going to let H equal, bless you, we're going to let H equal 5, right? Because the amount of change in the temperature, the amounts are 5 back or 5 forward, or 5 plus or 5 minus, whatever you want to say. I will point out, this is slightly different than problem 18, where if you're looking at the point where velocity is 40 and time is 20, let's see, velocity is 40 and time is 20. Going in this direction, you're increasing the time by 10 hours. Going in that direction, you're decreasing the time by 5 hours. So it's a different amount, right? It's not the same increase every time for that one. So it's a very slightly different thing when you calculate it. But you still, right here, you would let H equal -5, and here you'd let H equal +10 to get the amount added to the right or the amount subtracted to the left. That means you're going to divide by a different number when you find those average rates of change, essentially. So I feel like I'm doing way too much work here. So I'm going to do this one this way, and then I'll show you like the way I would actually do it for the next part. So from essentially, I'm thinking from a temperature. Fine, I'll just write it this way. Fine. So that's going to be, I'm going to, what did I say here? I'm going to approximate this by letting H equal +5 for the first time. Right? Those are the changes I have. So I'm going to get f of -15 plus 5, comma 50, minus f of -15, comma 50, divided by 5. And I'm just going to look at my table. So let's see here. Sorry, I'm kind of off. So let's see. F of -10, comma 50 is right there. Bless you. That's my -22. My f of -15, comma 50 is my -29. And the bottom part's 5. So I end up with -22 plus 7 plus 29, which is 7 divided by 5, which is 1.4. Or in other words, what we were saying here is if we let the temperature increase by 5 units, by 5 degrees, the wind chill is going to increase by 1.4, whatever the units are. That's what we're saying with that. Okay, the other way, so really we're just taking the following. We're finding the difference between the outputs divided by the difference in the inputs, right? The delta F over delta, whatever your input is, either delta T or delta V. So to do this other one, I would say the partial derivative is still at the same point. I'm just really thinking of taking the difference between these two values, the -29 and the -35, and then dividing by the difference in the temperature, which is still 5. So I would probably think of it this way. -35 minus -29 divided by the difference in the inputs, which is -20 minus -15. Or -35 plus 29 is -6 divided by -20 plus 15, which is -5, and that's 1.2. And then you average those. Which in this example, you could have gotten the same result by just doing that one minus that one divided by the differences here, because all the differences are the same. But if they're not all the same, like in problem 18, you can't do it that way. So this is why I'm showing you this longer way of doing it. So we're going to say that our FT at -15, comma 50 is approximately the average of those two numbers, 1.4 plus 1.2 divided by 2, which is 1.3. Feels like a lot of work, but it's really not that terrible. So let's do the other one in a more typical way. I mean, the other one meaning the other partial derivative. So now we're going to estimate FV. And let me just fold this up here so it'll make it easier. So, sorry, does anyone need to see that still? Let me cover it up so I can. So now, to approximate the partial derivative in the v direction at the same point, -15, comma 50, I'm going to do two calculations. So this is the first one, and then we'll do the second one over here. So it's going to be approximately. So now we're changing v. So we're either going that way or that way. So let's do these two first. So my output is -30 and -29. So it's going to be negative 30 minus negative 29 divided by 60 minus 50, which is negative 30 plus 29, so negative 1 divided by 10, or negative 0.1. Similarly, the partial derivative in the other direction, not the other, that's not the right word. Going to the left instead of going to the right, it's going to be negative 29 minus negative 27 divided by 50 minus 40, which is negative 2 divided by 10, which is negative 0.2. And if we average those together, we're going to say that FV is approximately negative 0.1 plus negative 0.2 divided by 2, which is negative 0.15. Or if we increase the velocity by 1 kilometer per hour, we will decrease the wind chill factor by 0.15 units. We finally have all the information we need to write the linearization. So now we're going to go back to the thing we said in the beginning. Their linearization was going to be that, and fill in all the values. So my linearization at t comma v is going to equal negative 29 plus my partial with respect to t, which was 1.3 after we averaged those two numbers together, times the temperature minus 15, plus the partial with respect to v, which is negative 0.15, well, that's our estimate of it anyway, times the velocity minus 50. There's our linearization. And again, I'll point out the hard part of that process in this example is the estimation of the partial derivatives. And again, I'll say to find them, I just like, so to estimate the partial with respect to t, I took the difference between these two values divided by the difference between these two values, and then the difference between these two divided by the difference between these two, and then average those two results. And similarly for v, I took the difference between these two divided by the difference between these two, and the difference between these two, or the average rate of change from here to here is the difference there divided by the difference there, and then average the two. And again, in this case, since all of your differences are the same, you could have skipped that and just done this, the difference between that and that and that and that. But for the other problem 18, you do have to do it this way because the differences are not all the same each time. And then the second part of the question, or the rest of the question, was to estimate the wind chill index when the temperature is negative 17 degrees. So we want to find or estimate f of negative 17 and a velocity of 55 kilometers per hour. Well, great. That's just going to be approximately our linearization evaluated at negative 17, 55. We plug in our values and we get negative 29 plus 1.3 times negative 17 plus 15 minus 0.15 times 55 minus 50. And then we could simplify this. It's going to be negative 29 plus 1.3 times negative 2 is negative 2.6. And then negative 0.15 times 5 is negative 0.75. So we end up getting this negative 29 plus 2.6 plus 0.75, which is some number, right? 31.6 plus 0.75 is 32.35, negative 32.35. Whatever those units are. They don't give us units for the wind chill index. I would guess it's temperature though, right? Because I think the wind chill index is be like how cold it feels with the wind chill. So if I had to guess at units, I would say degrees Celsius, but what do I know? Which makes sense though, right? Because if the actual temperature is negative 29, or sorry, negative, yeah, if the actual temperature is negative 17 and the wind is going at 55 kilometers per hour, it would make sense that it would feel a lot colder because the wind is going fast. All right, that seems plausible. Questions about that? Okay, so you should definitely try number 18 on your own if you're in Lee's class, or if you're, I don't think Varn's here quite yet, but yeah, that's definitely something I would encourage you all to do. Again, I know Lee does not collect homework. That doesn't mean you shouldn't be doing it, as I know you are all very well aware of, but I can't help but say it anyway. All right, where was I going next? The chain rule. Let's talk about the chain rule. Talk about getting my papers in order here. Okay, great. And it's really easiest to talk about the chain rule by just starting with an example. So the chain rule. Here's what we've got. The pressure, P, in kilopascals, and the volume in liters, which we'll call it, sorry, volume V in liters, and temperature, T, in degrees Kelvin, of 1 mole of an ideal gas, sure, we can pretend like we know some chemistry, are related by the ideal gas law, which says one way of writing this is that P times V is equal to 8.31 times T. I think the actual equation is about PV equals nRT, and I'm assuming at these assumptions, N times R is 8.31. Not worried about it. So here's the setup. If the temperature of a gas is 300 degrees Kelvin. You say degrees when you say Kelvin, or you say 300 Kelvin? Kelvin. Yeah, okay. I was like, that doesn't sound right. Yeah, 300 Kelvin and increasing at a rate of 0.1 kelvins per second. And the vol, I know it's a lot of writing, the volume. So one thing I'll point out is you don't need to write down all these words. You can, but really part of the process here for you kind of doing problems like this is distilling what's written here into what you actually need. If I was writing this down, I'd be writing PV equals 8.31 T, T equals 300, dt equals 0.1, volume or V equals, what is it, 100 liters, and is increasing at a rate of 0.2 liters per second. How fast is the pressure changing? Again, I would say if you read all that, here are the things you should actually write down. The equation, PV equals 8.31 T. The temperature is 300 Kelvin. The rate of change of the temperature is 0.1 kelvins per second. The volume is 100 liters, and the rate of change of the volume is 0.2 liters per second. Let me just make sure. Yep, increasing. Okay. That's the pertinent information. And then, oh, there's one more thing I say. And then they're asking us the question, how is the pressure changing? So we would say, oh, cool. They're asking us to find what the rate of change of the pressure is. That's the whole setup. So how do we do this? Well, this is where we need kind of a new idea about how the chain rule works. So the idea here, first is I'm going to take that equation, PV equals 8.31 T, and actually isolate P. So taking our PV equal to 8.31 times T, I'm going to rewrite that with P on its own equal to 8.31 T divided by V. Or preferably, since I know I'm going to be taking some derivatives, 8.31 T times V to the -1. Seems like a better way to go. So a couple things. Pressure is a function of both temperature, and volume. But both of those, temperature and volume, are both functions of time. The way we model this is with a mapping. So the way I think about this mapping is you're kind of starting at the top with the thing that you're kind of interested in. So we want to know how pressure is changing. So we're thinking, okay, great. Pressure at the top. At the next level down, pressure immediately depends on, well, if we look at this equation, we see that pressure depends on temperature and volume. So we're going to say, okay, pressure depends on both temperature and volume. And then the next level down, temperature and volume both depend on time. Since it's the same, we're just going to draw two little paths that go to the same lowercase t there. So here's our mapping. And now we can see that what I would say is there are two paths from P to time. And the chain rule says for functions of more than one variable, says, here's what I'm saying in words, says you have to take all the paths from P to T if you want to find the derivative. So you get from P to little t, right? Little t time, not big T temperature. So to get from P to temperature, we're going to take the derivative. So that's going to be del P del capital T times, then to get from capital T to lowercase t, the derivative there. D capital T, D lowercase t. Yes, it is a del there and a D there. Because it's a del here because P is a function of multiple variables. It's a D here because temperature is a function of only one variable, time. Again, not super important, but it's nice to be precise. And then the other path. The other path is going to be del P del V, the partial derivative of P with respect to volume, multiplied by dV dt, the rate of change of volume with respect to time. And all of that together, all the paths that get us from P to little t added together is the derivative of capital P with respect to time. Whenever you have a situation like this, really the first thing you want to do is draw the little map, which we'll practice doing in a few more examples. The rest of this process is then just plugging in the things that we know. So if we're trying to find the rate of change of pressure with respect to time, well, we know all these other pieces. We know what we don't know them yet. We have to find them. Sorry, we don't actually know them quite yet. 1 second. So our dP dt, well, taking the derivative of P with respect to T, it's going to be 8.31 times V to the negative 1. Then I'm actually going to plug in, yeah. Sorry, that's too many capital T. It's terrible. My DPD capital T. These T's are terrible. Sorry. It's a del. Holy smokes. See, this is where I'm getting caught up now. Sorry, it's that. And then we plug in V equal to 100 because the volume is 100. And we get 8.31 divided by 100 or 0.831. I feel like I've got some weird things going on over here. Oh, I see what happened. Okay, that's fine. Yeah, okay. Sure. 0.0831. Yeah, I know. The numbers are not nice. And then similarly, DVD. God, sorry. I'm trying to find this part now. Del P del V. Taking the derivative of this with respect to V, it's going to be negative 8.31 times T times V to the negative second. And then you're going to plug in T equal to 300, V equal to 100. So writing it all down, thank you. Writing it all down, we're going to get the following that our actual derivative that we want to find. All right, our dp dt, and this is what I mean to write, is going to equal my this. So that's going to be my 0.0831 times my dt, which is the rate of change of temperature, which is what they told us was 0.1. Plus this part here, my del P del V is going to be negative 8.31 times 300 times 100 to the negative second power times my dV dt, which they told us was 0.2. Again, just to kind of make sure we're all on the same page here, this is my del P del T. This is my dt d little t. This is my del P del V, and this is my dV dt. And if you add that all together, you end up getting negative 0.04155 approximately kilopascals per second. So if we increase both the volume and the temperature at these particular rates at these particular values, we end up decreasing the pressure. Okay, that seems plausible, right? If the pressure is equal to 8.31 times the temperature divided by the volume, well, increasing both of them could end up with either the pressure increasing or decreasing, right? It's not super clear from the get-go until you actually plug in the numbers.
Right, like when you did the partial derivative of P with respect to V. I'm just kind of confused how if we get negative.
Sure. So I was looking at this equation up here, which is 8.31 times T times V to the negative 1. And then I took the derivative of that with respect to V. So the 8.31 T hangs out, and the derivative of V to the negative 1 is negative 1 times V to the negative second.
Okay.
That's what's going on. But yeah, it was kind of like way far away from it, so it was hard to see what was going on there. Other questions about this? Yeah. That's a good question. I don't know if I have a good answer to it, to be honest. I unfortunately don't like it. This is the way it's defined, and so like maybe the next class when we come back around, there's an idea we're going to come back around to, which might help us understand more why the chain rule works the way it works. But I don't have a good explanation for you right now, unfortunately. It's just there's something else we need to see later, and then we can kind of come back around and be like, oh yeah, that's why the chain rule works that way. But for today, just take it on a little bit of faith. I know it's not usually my vibe. Like I usually like to be like, hey, this is why it works. But the reason it works this way is because that's how we define it to work. And sometimes, unfortunately, that is how math works, is because we decide we're going to define it to be this thing because that's what we all want. But there is more to say about this, just not today. Other questions aside from that? Let's look at another example. Make sure I keep my notes in there. I do like that example because it's like a real world example. Like, right, if you increase the volume and the temperature, will act, with these numbers at these amounts, you will actually get this decrease in pressure. So it's a real example of a function of two variables that would work this way. But most of the time, we're just going to have like functions of x and y and whatever, and the usual kind of things can happen. So let's look at this next example. Let's say we have the following. Our function of x and y is equal to x cubed times e to the 4y. And we're also given that x is equal to cosine of t and y is equal to sine of t. Often at a very base level, everything ends up being a function of t because we usually think of t as time or just some parameterizing variable. So we want to find df dt in two ways. the first way by writing f as a function of t and then just differentiating. In fact, actually, this will maybe show us why it works. Not maybe, it will kind of show us. So first we're going to write f as a function of t and differentiate. Differentiate. I can write the whole word. Okay, so let's see. So we're going to write f of x comma y is now going to be, we're just going to replace x with cosine and y with sine. So it's going to be f of cosine of t comma sine of t. And that's going to equal cosine of t cubed times e to the 4 sine of t. And this is now what we're thinking of as f of t. Right, we can fully write f as a function of t. Okay, we're going to differentiate this thing, and we're definitely going to have to use the product rule. So we have a function of t here times a function of t there. All right, so let's see. So f prime of t, or df dt if you prefer. The derivative of the first part, so the derivative of cosine of t cubed is going to be 3 times cosine of t squared times the derivative of the inside function, which is negative sine of t, and then times the other stuff left alone, e to the 4 sine of t, plus, then we switch it up. We leave the cosine of t cubed alone, and then we take the derivative of e to the 4 sine t, which is e to the 4 sine of t, times the derivative of 4 sine of t, which is 4 cosine of t. And yes, I'm sure we could simplify this, and we really don't need to. So now let's do it the other way by using the chain rule. I'm going to draw my little map. F depends on x and y. X and y both depend on t. So my df dt, or f prime of t if you prefer, is going to equal del f del x times dx dt plus del f del y times dy dt. Okay, let's write it out. So del f del x. So looking at the original f of x y equal to x cubed e to the 4y, the partial of this with respect to x is going to be 3x squared times e to the 4y multiplied by dx dt, which is the derivative of cosine is negative sine of t, plus del f del y, which is going to be x cubed times the derivative of e to the 4y, which is x cubed e to the 4y times 4 times dy dt, which is the derivative of sine of t, which is cosine of t. And then to fully see the answer, we have to go back and plug in that x is equal to cosine and y is equal to sine. Doing that should end up exactly with the same answer here. Let's do it just to be sure. We're going to get 3 times cosine of t squared times e to the 4 sine of t times negative sine of t plus, it's kind of gross, cosine of t cubed times e to the 4 sine of t times 4 cosine of t. Are those the same? You bet. You can look 3 cosine squared, negative sine, e to the 4 sine, cosine cubed, e to the 4 sine, or cosine. Same parts exactly. Great. So there is maybe a better answer to your question than what I said before. We can do it either way and still get the same result. So that's why this formula works. Because essentially, if you plug in the functions of t, you end up using you have to kind of use the product rule because you've got things multiplied together, and that's what the addition is coming from. Cool, it works. All right. Let's look at a couple more examples so we're not limited to just this type of path, right? It'll often be where your top function is like a function of two variables, and then each of those two variables depend on one thing, but that doesn't have to be that way. You could have a lot of other different mappings. For example, also, if you have questions, that you're welcome to ask them. Happy to explain more. So for example, you could have something like W as a function of x, y, and z equal to x squared e to the y cubed over z. That's gross. If I was going to deal with this, I would definitely do myself a favor and rewrite it as w of x comma y comma z equal to x squared e to the y cubed times z to the -1. If I know I'm going to have to start taking derivatives, I know I don't want fractions. I'd rather have negative powers. It's just going to make my life easier. So then, and we're also told that x is equal to t squared, y is equal to 3 minus t, and z is equal to 4 plus 3t. And we're asked to find dw dt. So here's our pathways. W depends on x, y, and z, and x, y, and z all are functions of t. So we're going to have three things added together. dw dt is going to equal del w del x times dx dt plus del w del y times dy dt plus del w del z times dz dt. All three different paths that get me from w to t. And every time you go from like a level to the next level, you're taking the derivative, right? To go from w to x, we're taking the derivative of w with respect to x. To get from x to t, we're taking the derivative of x with respect to t. That's where we're getting del w del x times dx dt, and del w del y times dy dt, and del w del z times dz dt. Just all the pathways to get us from the top to the bottom. And then we just have to fill in all the things, which just gets kind of gross. So let's see. So dw dt is going to equal del w del x, which is 2x times e to the y cubed times z to the -1 times dx dt, which is 2t, plus del w del y, which is, that's not actually what it's called. X squared e to the y cubed z to the -1 times the derivative of y cubed z to the -1, which is 3y squared z to the -1 times dy dt, which is -1, plus del w del z, which is again x squared e to the y cubed z to the -1. But now when we take the derivative of this top part, we're differentiating with respect to z inverse, so it's going to be y cubed times -z to the -2 times dz dt, which is 3. And then really we're not going to, because I don't want to, but then you should plug in x equal to t squared, y equal to 3 minus t, and z equal to 4 plus 3t. So that your answer is in terms of t.
Say after 2t plus x squared e to the.
So it says
That's 3 over z.
it is e to the y cubed times z to the -1. So no, not always, but mostly yes. So again, when do I use the partial derivative? When the function depends on more than one thing. When do I use a regular derivative? When the function depends on only one variable. In fact, let's look at this next example, which kind of exemplifies that. So yeah, I don't have enough room. So yeah, we got time. So here's another example. Let's say we have, sure, z as a function of x and y equal to inverse tangent, or if you prefer arctangent, of x plus 3y. And we're also told that x is equal to r cubed times t, and y is equal to r times the natural log of t. So let's draw our map. Oh, and then we're gonna be asked to find two things. We're gonna find both del z del r and del z del t. Because here, even at the base level, z depends on more than one variable. Let's draw the map to see that. So the first part, at the highest level, z depends on what two variables? Right. And then at the next level, x depends on r and t, and y also depends on r and t. So I can draw x depending on r and t, and also y depending on r and t. Oh, sorry, yes. Oh, yeah, let me zoom out. Yeah, sorry about that. Apologies. There you go. Now you can kind of see it. So if I wanted to first find del z del r, well, once again, it's just all the paths that get me from z to r. So it's going to be del z del x times del x del r plus del z del y times del y del r. And they are all del's here because each function is a function of more than one variable. Z depends on two things, X depends on two things, Y depends on two things. So all my derivatives are partial derivatives. And then let me just do it. So the derivative of the inverse tangent of some stuff or the arctangent of some stuff is 1 over 1 plus that stuff squared. So we're going to get 1 over 1 plus x plus 3y squared times del x del r, which is going to be 3r squared times t plus del z del y, which is also, oh, you know what? I forgot something. No, I didn't. I just didn't. Well, I forgot to say something. I forgot about the chain rule there, right? The derivative of inverse tangent of some stuff should be 1 over 1 plus my stuff squared. I got lucky because here the derivative of my stuff is just 1, right? Derivative of x is 1, derivative of 3y is 0 with respect to x. For the next part here, same beginning, the derivative of inverse tangent of some stuff is 1 over 1 plus that stuff squared. But now we have to multiply by the derivative of the inside stuff, and we're differentiating with respect to y, so it's going to be 0 plus 3. And then we're going to multiply by the derivative del y del r, which is going to be 1 times natural log of t. Nice. And then again, you can go plug in that x is equal to r cubed t and y is equal to r natural log of t to have a more satisfying answer. I don't know. Usually we don't do that, to be really honest. Like we just usually leave it here because you know what? Everybody reading your work here knows that x is equal to r cubed t and that y is equal to r natural log of t. It's written right on the page. So they can also just see that, yes, we've done the right thing. And if all of us wanted to, we could plug in that for x there, and that for y there and there. But there's really no need to. Why don't you all try finding del z del t?
So every time we try to cancel out the third one we fucking brought in.
So I wouldn't say we're canceling that amount, but yes, that's the idea. In fact, that's something I should have pointed out is when you look at this, if you could treat these like fractions and cancel things out, you should have just exactly del z del r and del z del r because you can think of the del y is canceling and the del x is canceling. And that's true for all of the partial derivatives we've done, or all these chain rule ones we've done. All the things that don't look like the end result that we want should cancel out. It's kind of cool. It's a nice way. It's a very nice way of thinking about it. Good observation. The nice part about this is half of the problem is already done for us, right? This piece here and this piece here, right? This sorry, not you. This here is already our del z del x. And this here, including the 3, is already our del z del y. So half the battle's already done. We're going to get 1 over 1 plus x plus 3y squared. And then we have to multiply by del x del t, which is going to be r cubed. Sorry, can't see that. R cubed. Plus del z del y is, again, just this part here. It's 3 over 1 plus x plus 3y squared times dy dt, which is r times 1 over t. That's it. Really, the reason we're talking about this is because we need this to then talk about how to define directional derivatives, which is like a partial derivative, except instead of being in the x direction or in the y direction, it's any direction you want. There is one other cool thing we can do with this, and I think we have enough time to say it. So let's do that real quick. So one neat thing about the chain rule is you can actually use it as a shortcut for implicit differentiation from 17a. So for example, if I said I wanted you to find dy dx for the equation x cubed plus y squared plus x e to the y equal to 7, the way we would have done that in the past would have been to just differentiate with respect to x. So take the derivative, differentiate with respect to x. We get 3x squared. We're assuming y is a function of x, so the derivative of the derivative of y squared is 2 times y times the derivative of y. And for x e to the y, we have to use the product rule. It's going to be the derivative of x times e to the y plus x times the derivative of e to the y is e to the y times the derivative of y equals the derivative of 7, which is 0. Then you would leave these two things on this side, bring the other two things to the other side, and might as well factor out the dy dx there and say, okay, cool. Dy dx times 2y plus x e to the y is equal to negative 3x squared minus e to the y. Actually, I'm going to write it as negative 3x squared, so negative of 3x squared plus e to the y. There is a reason for this, I promise. And then finally, we would divide both sides by 2y plus x e to the y to get the dy dx is equal to negative 3x squared plus e to the y divided by 2y plus x e to the y. But now, there's a new way of doing it. And the new way is the following. Where my notes go? So what we're going to do is we're going to remind myself what I'm doing. We set it always equal to 0, right? Yeah. So what we're going to do is we're going to bring that negative over to the other side. We're going to say x cubed plus y squared plus x e to the y minus 7 equals 0. And we're going to call this entire left-hand side f of x comma y. So I'm going to take the derivative with respect to x of both sides of this equation. But I have to use the chain rule because f depends on both x and y, but also y depends on x, right? We're making the implicit assumption here that y is a function of x. So if I differentiate both sides, well, the derivative of the right side is 0. The derivative of the left side, well, I need my two paths. I need my del f del x, but then dx is just 1. And then I need my del f del y, and then times dy dx is the thing we're trying to find. And then if we solve for this, we end up getting that, and I'm going to call this, I meant to use different notation here. I'm going to call that fx, not fy. We're going to get that fy times the derivative I'm trying to find is equal to negative fx. So then dy dx is going to equal negative fx divided by Fy. And look, if you look at this original expression, my partial with respect to x is going to be 3x squared plus 0 plus 1 times e to the y minus 0. And my partial on the bottom, my partial with respect to y is going to be 0 plus 2y plus x times e to the y minus 0. Oh, look, it's exactly the same. So this is a shortcut for the partial derivative. And generally we would say that dy dx is going to equal negative fx over fy. And it works basically whatever variables you're using. So if there's more variables involved, like if you want to find like del z del x, it would be negative fx over fz, and so on and so on. We'll talk more about this on Monday, but I wanted to show you one quick example. And this formula is definitely in the textbook. We don't use it a whole lot, but it is kind of an interesting application of the chain ruler.